Добрый день. Еще раз я рада приветствовать следующего докладчика.
Denis Smirnov, next speaker, the developer of Metadata. He will tell us about Greenplum. What is Greenplum? Has anyone used Greenplum in? Great. For the rest, who didn't use it yet, this is fork of Postgres that was done a long time ago, and currently it's released in open source in proprietary status. That's what it has. The main meaning is to work with analytical load. So the Postgres is a classical vertical scaling management system of database, which is specifically done for online transactions, and we can prove it very easily. When you look at the access methods in the initial codes, they will be the indexes, and indexes, this is a good meaning for LTP load. For the analysis, it doesn't help much, because we have lots of different tables with hundreds and billions and trillions of different messages. So we need to do joins and aggregates, and this can be worked with processed very effectively. If we look at all the analytical management system of database, they all built up in a similar way. So what should we do first of all? First, we break them in clusters, because the machine cannot scale vertically, and it's limited. So then we need to do it horizontally, and then second of all, then we need to the engine of the storage engine. In all these methods that we exist in Postgres is not enough. And then one of the important requirements when we do the analysis, most of the data, they are stored in different systems. It cannot be only Hadoop, but other systems as well. So this data need to be retrieved in a free manner and be analyzed afterwards. I wrote the list of what Greenplum is, and there is one scary line which says Postgres 9.4. The Greenplum has two different versions. The first one is 5 for the core, 8.2, and version 6, which is being built in long-term alpha, is based on 9.4 version. When Greenplum was forked, it's been developed a little bit aside, so the core hasn't changed much, even though it was not that well, but the wrapping was changed completely. So when we opened it and we tried to synchronize with master branch of the Postgres, we decided to bring the changes from Postgres to Greenplum, because it was hard to import from Greenplum to Postgres. One of the clusters, which is based on MPP, master build, and Polymorph storage, entering other systems for making the analysis. And it has own network protocol, the system of distributed host, and the access methods. Thus, we have this scheme of the cluster. The clusters can be of different types. How do we make the cluster for each of the load? You can make it yourself, but if we look globally, we have different approaches. For instance, the cluster can be homogeneous, or they have the roles where all nodes of the clusters are similar, or some of them can be step, and we have some role, and does have other roles. This is what the module looks like. It has only the examples of management system or fault-tolerant groups. These fault-tolerant groups can be automatically fail to bring some algorithms or raft to pathos, or some external manager that brings them up in case of the failure. As for the Greenplum, it looks like that. This is the cluster based on the roles, This is the failure tolerant groups, and some of the groups and all of the groups, they have the external switch. How does it look? We have two roles. One of them is a master role, which has the name of dispatch, and it includes the master and hot reserve and hot replica. It's used manually, so to manage the failures, it's switched by the operator. It's connected to the abstractor of protocol of interconnect protocol. It's on some sort of instance that you can retrieve the statistics from. And then the failure tolerant dispatch group, which manages other groups that storage the data. That's his execute group with the segment Miro segments. The segment and Miro differs from master and redundant reserve, has a hot redundant data, so it's written with its own protocol, which is called change tracking, and it is not written because in Oracle and Postgres 8.2 there is no hot reserve, and in 6 version it's the situation is different, and Postgres execute is being used. So the master is actively participating, and it's external view observer which does the switch which is transparent for the operator. If we lose a segment, it's not a catastrophe. It's automatically it's running very well, and it can be scaled line scaling. So there is some discussion going on. I think it's the law of Amdahl law. When you have a distributed system, you have some lineup calculation. So if the lineup calculation, they are not parallel. As more this part is, the more sad this graphic looks like. So it shows the speed up based on the calculation. So no matter how many calculations you have, the speed will not increase. In Greenplum, I cannot imagine how you can calculate it beforehand, but with some of the queries, I know for the fact that when you increase the calculation, it will not increase the speed. And for the limitation of the growth of the cluster, there are some other things that have to do with it, but I will tell about this later. So in Greenplum, it's a transaction system compared to other analytical solutions. Thus, if we look at all this scheme, from the upper part we see the master, which manages all, and then a network abstraction. We added the segments to this through interconnect. Every node, which is mentioned here, is the cluster of Postgres, is propatched. So the master node has the very distinctive peculiarities as the manager of distributed transactions. Each other nodes have local transactions, and the manager has distributed transaction. All the rest looks pretty much the same. And how the transaction is being done. One of the nodes, incoming node, is the host master, and you can operate the cluster only through this node. And all the rest is in the same way. When we have the query, the parcel of the trees is processing it, and then it goes through the optimizer. We have optimizer on Levis, on Postgres through patch, and the second one, Pivotal Oracle, which is outsourced, and you can compile it with that one. Oracle is not always better than legacy. I think it's not always better than legacy. And then through global book, you can always switch to the optimizer which you like to use. And then they go through the dispatcher. This query goes to this, is divided by the segments, so it's got like map phase. And then we bring the results back to the host master and create or process the reduce. So the total results we compile it in the master.
The distributed query looks like this. In fact, the whole distribution and execution of the query is made by master. It lives a very active life in every segment, and it creates such things as a slicer on each step. A separate Postgres processor are created which make the part of their job, and they contain some additional nodes of the plan which do not exist in a conventional Postgres. Also, there is a separate structure which is called gang in the master, which record the slices which are operating, and as they are executed and utilized, they are being removed from there. The resulting output would be the combination of all resulting slices. Slice root, slice 0 will contain this information and have the reduce phase. The whole architecture is designed for analytical load, and the main problem is to pull in data or pull up data because there are too many data. So it's not possible to bring them through one single node. So the whole infrastructure looks as a sort of a management tool which has a lot of pipelines to source data and to give them back. Under the hood, we have this special access method, the separate access method, which is called external table, which is quite simple. If we take a global look at it, in fact, it has just an additional library which allows to work with it through the file protocol. Every instance of Postgres can work with post data on it. As a result, we have this system with parallel unloading and downloading of data. We have a framework inside the Greenplum which allows to implement different protocols, and in course of our operation with this libcore. So roughly speaking, based on which agreement we send packages in the system. You can write your own protocols, but there are two the most common and popular protocols for those who work with Greenplum. First is GPL dist. It's normally used in the system with ITL host, and we uploaded a lot of files to the system, text files. We hid it under some web server called GPF dist, which can communicate with Greenplum segments in REST, and this utility knows how many segments are there in the cluster, and it distributes necessary data chunks. The second thing, which is also well known, is PXF. It is basically a sort of a Java-based service which is installed on the host, and one hand towards Greenplum through REST and towards the systems through Java API. So Greenplum has its own protocol which supports communication with PXF service, and inside PXF it's possible to write your own jarnex which will tell how to work with external systems. For instance, if it's some single node Postgres, then it's quite straightforward everything. If it's a HDFS, so we would like to suck up data with different data nodes of this HDSF. So PXF allows to extend Greenplum functionality very well. As a result, based on this PXF, it is possible to make which is called Polymorph storage. As a result, it's the same idea as database wrapper, but just realized in with a different method. We can create partitioned or sectioned tables, and the part of sections of which will be external tables. They do not store data, and as a result, they are just indicators to some external systems. Warm data can be stored in Greenplum. Hot one can be in cache, in memory cache, and cold data can be stored in some Hadoop. And from the point of view of the operator, it would look like a single table. So the planner can rewrite a request, and in case of any problem, will go to a table and to retrieve from the system only necessary set of data under certain conditions. And the PXF is not able to provide aggregators. Some few more good features in the external system. Is not possible to gather statistics. So unfortunately, in Greenplum, there is a hardcore 1,000 blocks, which makes the life set for everyone, and it's not rewritten. What else was done there? Network protocol, web protocol. First realization was made on TCP, but it didn't work because there were big delays to set up connections between all segments, all slices during the distributed query. It was quite painful, and it was rewritten to a separate protocol with the stream control. And in terms of its throughput, it is the same as TCP, which is not a bottleneck, but in terms of the connection, it looks much better. There are some problems, some issues sometimes if we make a very big amount of segments on one host, and here we could have a very sad story when we just lack ports. We don't have enough ports on our hosts, so we have a very small problem we try to address. For instance, when testing 200 segments at 30 hosts, we arrived at the lack of ports in our operating system. Then what else do we have? We have the resource delineation. When we have heavy queries and lots of them, someone is uploading data in big batches. Somewhere we have very complicated aggregations. Somewhere analysts do some simple queries in ready-made showcases. It looks ugly, and there are a lot of context switches, a bunch of issues, and we want to delineate it all. Initially, we had an old solution called resource queues by Greenplum resources. Then it was rewritten, and now the resource groups are used. It is a superstructure over C groups of Linux virtual file system, which allows access to the core entities. And so Greenplum has the management which goes through this virtual file system, and all new groups and some new groups are created there for CPU, for memory, and data are distributed between these groups, which evoke as a result of every query. A user, Greenplum user, can be connected to a certain group, and all bids and all hosts to be created will be placed into these resource groups in the necessary section of these groups. As a result, we get a quite nice picture. Some resource groups can be pinged by a cause, someone by the throughput or by bandwidth. In terms of memory, there are also limits. There are some parameters which determine when we start to dump it to disk, and in parallel to transaction it can be determined and evaluated, and this piece improves the performance of the loaded cluster very well. Now we finished with the cluster, and we start talking about access methods, which are related to the analytical load. What is the point of analytical load? First, we have one or several very wide tables, hundreds of columns and very, very many lines. And when we work with data, we work with them in big packs. We make batches not in one line, but thousands, dozens of thousands, millions of lines in one batch. And when reading, a lot of lines are being processed, but very few columns. In a typical scenario, we have 300 columns, but only 3 take part in it. It's only 1% of the whole table. When we read data in MPP, we determine the width by length, and if we take the square, or what we read in MPP, and if we work with columns, so we have only 1% in terms of width. So we can good savings there. Then the final result of the query is small versus the total amount of data in the table. Sometimes it's either scrolls or filters, or only a few parallel requests and delays when getting results. This is analytics. We do not need to pump the response time. We need the proper throughput. How can we solve this? Normally, the storage engine, which should be suitable for this, does the following. First, metadata are segregated from the values. Next, the column engine is created. Then compression of columns. By the way, it works very well because in one column there will be one type of data. We also have it. Also, we have a pattern that blocks are created in a certain way in columns. They're being sorted, and disseminated indexes are connected to them, but it's not existing so far. It doesn't exist so far. Then sectioning, partitioning, segmenting, and let's take a look. What can we tell about it? What about metadata? If we had a simple heap table, we had a table, and in every tuple we have ACC and some him bits which allow to work line by line with index. So the prefixes in big batches will be identical for this metadata, and it would be stupid not to save on that. For every pack, metadata are similar, so they are being stored in an external storage in one pack. What comes next? Columns. If we have a trop-based engine, line-based engine, so this story about 300 columns and we need only 3, then the red will be useful information, and the yellow is just the total amount what is calculated. We calculated tuple by tuple, and then we just unpack them and insert in necessary columns. It's very suboptimal for the big load where we work with a small number of columns. We wish it was like in the left part when we read only columns we need, and the chain of files is in the physical file system is created for every column. How is it realized in Greenplum? In Greenplum we have an engine called append optimized, which can be suitable for columns and for lines. For line, we imply that metadata are placed separately and are stored in a different place, in different location. And besides everything, this engine supports compression. So I tried to outline how it works. Under the hood, it looks in the following way. Let's take the line engine, which is easier, but the column will be similar plus information containing which segment belongs to which column. It looks in the following way. When we open the transaction and start populating a table with the data, start writing, in each segment we create a separate segment file where we start to write consecutively all necessary data. It is built of certain blocks. For example, in HPI, as far as I understand, it's like a page-like organization. Here we don't have pages, we have other structures called blocks. So we start to build this file out of these blocks. When we commit it, we take some additional heap table and we just bluntly write indicators to this table. We write that this table belongs to this segment file and this is the end of this table. It is located here. This scheme has a lot of disadvantages. For instance, parallelism. What if we want to write some parallel transactions to one table? So we create additional segment file in this case and also write information there. So there could be 127 files for the line table, and the 01 is registered for some service operations. Besides that, we have additionally a heap table which is attached next door, which contains a map of shifts inside each block containing the segment file. This is needed to make Postgres index work through this abstract. Post indexes are normally not used, but if you badly want it, you can use it. And there is a third additional table which contains the visibility card for every segment file. As a result, if we make an update or delete, we add new data to the end of the segment file and we place just a mask to this table which covers non-visible data for us. Just in brief, that was all. Now, and I forgot one important thing, those blocks segment file are built of can be different for different load. For columns they are optimized in a certain way, for lines in a different way. So these blocks contain a header and some data. Headers, by the way, contain information about the type of the block, whether it's compressed or not compressed, and they control some of this block. As for the compression now, compression is only the leap and the STD. In the STD and the leap will be in the top 6. You can take a look how it works with data. Just for the experiment's sake, I created a very simple table. So if it's heap, then the size is about half gig. If we make append optimize line table, then we have 325. If we attach compression, then it's been compressed to 70. If we make column based without compression, 191, and with compression 57. So basically we have a great compression, a great deal of compression of 8-9 times versus heap. If you want to calculate the analytical load, if you would read it from heap, it would be really sad. We had to read 1/2 of gig, and here for the same data, we have to read just less than 60 meg. Well, it will be much, much faster. As for the sectioning and partitioning, as we may call it, normally in OLTP, partitioning is used to create indices in the operational memory. Here, the story is a little bit different. It is just about some limitation for consecutive reads. If we didn't have sections, we should read the whole table, and we want to cut it somehow horizontally, and for that we need these sections or partitions. Partitioning in Greenplum can be two types, by ranges and by lists. There are no limitations for attachments or enclosures, just for some details. In one level there could be only 32,767 sections. It places some constraints on our handling with this, and the higher the level of enclosure, the faster will grow the number of sections. Segmenting or sharding. I was really surprised that sharding in the academic literature is called segmenting, and when I call host segments, it should be read as shards. We take one virtual table and we decompose it line by line into different hosts. There are different policies of this segmentation, and so they are showing how to physically place every line to every shard. So in these 5 there are 2 policies. One is random, round robin. It's just for every block of these keys some some hash is calculated, and depending on it we send it to the necessary shard. In the 6, by key we calculate it for the key and then send the information. In the 6 we have also replicated for reference books to make them locally stored on each shard, which would be very good for joins, and we will avoid data redistribution. So as for hashing, in the 5 we use single instruction multiple data algorithm. This is hardware acceleration and full distribution by host and for joins. That's why joins in Greenplum work a little bit faster than in normal Postgres.
And because of this, we can speed up. In version 6, the joins have the same single support, and the distribution hashing is constant. So when adding, distributing new nodes, the cluster is distributed with an n figure. Then the cabbage thing, first the after vacuum is on default, and then locally the of shader. And then you do not know what to expect when the outer vacuum would start. And the distributed cluster, the MPP this time, is calculated with the slowest segment. And because of the Murphy law, we had lots of garbage, and we turned off the outer vacuum, and with an exception of template. So it was less of transactions, it was in batches, and we did it manually from the master. We would start up vacuum or a freeze, and it would, all the segments of the cluster starts operating at the same time, and each person will read its realization connected to the description. Please join us. This is one of the Greenplum. Can pay attention. There is a PIM message for you. So if you have any questions, thank you very much for your presentation. Please raise your hand, those who want to ask questions. Thank you very much for your presentation. It was the first time, it's like a new introduction into this space, into this topic. Did I understand you right that the master is mostly occupied with preparation of the queries and aggregation of the received data, and the main load is taken by other nodes? Is that correct? Yes, it is so. So if other nodes fails, then with the help of the master, you can do the failover. Yes, this is right. The master completely manages the failure tolerance group, and if the master fails, then it will switch automatically to either one. So what do you think in real life? What would be the number of the master and the number of the nodes? The scaling can be done by hundreds, more than hundreds. I can't say thousands, I'm not so sure, because I haven't worked with such clusters, but hundreds of those for sure. This is for version 5, correct? Yes. Thank you very much. Thank you very much for the question. Okay. We need the microphone. Thank you very much for your presentation. You've mentioned that B-plan hasn't been optimized mostly for the legacy, as Ruben, and as the cloud storage. What about some external outside of storage that make a limitation and do not allow you to create the system from or optimizing the time before the first line and next line? Or maybe there are limitations for the size of the results. If you do not support, instead of the grouping, maybe the limitation, that sort, please specify your question. There are some analytical systems that do not digest the result sets. So if we do the regrouping, there is like millions of or billions of specific figures. No, it will. Everything starts to put and everything becomes slower, but it will go to the disk. What if there is a variant with within Postgres? I know that it's possible if you have a sorted table, then aggregation, like with merge band and aggregate group, will use the fact that it means sorting. It will be sorted by index. Thus, the indexes are very rarely used because the index usually takes more space than the table itself. Well, for example, I'm not quite sure how your segment is operated, but maybe it's a Parquet file, but during the creation with ATL, you can segregate it by the columns. If you know exactly that it's sorted by the columns, now we only have primary key that exists in the table, and this is all. This is the only thing you can use. If you want to group differently, the reading is done in order, and then the optimization, the following optimization does not exist. Thank you for your question. Hello. Thank you for your presentation. On the other side, please look right. Yes, I see you. Just a small remark and a question. As far as I heard, 6 alpha has been upgraded to 9.6, I think. Well, to tell the truth, 2 months ago it was 9.4, so based on what I've seen from Pivot in the announcement, I think we'll have only 7 on 9.6. This was my question. Is there a hope to see not alpha, but a normal, stable release? Yes, there is hope. We are eager to see that release as well, just like you. Not long ago, I think they merged it, no? Okay, thank you. Denis, thank you very much for your presentation. My question is about merging and commitment from Progress to Greenplum. Did I understand it right that if we have some sort of bug in 9.6 version of Postgres, the same bug will be in Greenplum and we will not be able to fix it? Or do you have some fixed codes that the core of the Greenplum has not been updated yet, but no, only the ones that shoot you hard. The bugs that we find easily, yes, first of all, we find them in fork, and if we are able to fix them, and then merge them into operation form. So what about the critical bugs? Only the critical bugs. Thank you very much. Okay, the last question. Thank you very much for your presentation. Do you have some types for column storage, some types of coding, the coding with vocabulary, delta coding? And second question, do you have some vertical operations? That's a good question. We only have compression with STD and nothing else. Thus, for the vertical operation, the only thing that we can use, the only place we can use the vertical operations is a story how this single abstraction of correct. So currently we have it only when calculating the hashes and nowhere else. So this is not a ClickHouse. It will be 5 times slower than the usual one. I just wanted to clarify that inside of your tuple is it storage like in Postgres and lines when you send it to the external or cross regions. I cannot tell you how does the CH code for the compression of which node is working, but I can tell you how it is stored on the disk. Unfortunately, this is all I know. On the disk, it is the column storage, and each file has some sort of part of our tuple. And after that, all the columns are gathered together in the view that we need. How it's being realized, how it's been implemented, unfortunately, I do not know. Thank you very much for your presentation. Based on the internal architecture, how do you do the recharging for additional when the additional nodes are added? It's possible. We have some extra utility, a separate utility. So when we add some additional nodes, the new data are written and distributed among the new nodes, and the old table we think is not correctly distributed. So we will do the redistribution by the chunks with some stops, and then we do the redistribution until we distribute all of them. This is a full volume. And version 5, yes, we do, but in version 6, it's one n node plus n, and we distribute that n figure. And version 6, look at the constant caching, the code for the caching. Please look at that. Thank you very much to all the participants. You continue voting for the presentation that you liked, and the speaker with this presentation will get the prize.